Hi, and welcome to Who's Going to Secure the Code Our Army of Robots is going to be writing. My name is Arshan Dabirsiaghi, and I'm sorry that we're getting off a little late, but I appreciate you sticking around. I've been working in, where code meets security my entire career. I develop open source tools. I was a practitioner doing code review and pen testing, and I've made security tools in the past. And that's the experience that I'm bringing today. Uh, a lot of people are probably familiar with Copilot. Copilot is what we call a fill in the middle sort of product. It's essentially autocomplete. It's really smart autocomplete. I'm a user and a fan, and it's definitely the most widely adopted, generative AI tool in the development space. And when the big companies you see listed on the bottom here have started to study it, they found that it helps generate between 25% and 60% more throughput. So one developer is developing 25% more code. 60%, that range does not feel right at all to me as a power user of Copilot. Definitely 25% sounds more like my experience. And then if you have been, getting the updates from Copilot in your IDE, you'll see that they're turning a little bit more into assistants, these lightweight assistants that can draft whole new sort of components, more like things like, give me a file that does this. It is sort of one file at a time. And this is getting more popular, but the statistics on the adoption we don't know. And then what we also don't know, how will this help with the throughput? If autocomplete is giving us 25% more, and we can now have an assistant in our IDE drafting whole files, that is interesting. And I think I'm just going to pick some numbers out of thin air here. No matter what number you want to come up with, you can use for your own mental model. I think we're going to still end up at the same place. So I'm just picking 100% again out of thin air. And then now, if you watch the end of the GitHub keynote very closely, GitHub Universe keynote, they flashed something on the screen very quickly. It was a Devon like feature where you could open up an issue and have the Copilot go sort of add a feature. Across many files, across your dependencies, across all of the stuff that you might want to edit in a repo to bring a new feature to light. Now, if autocomplete gives you around 25% more throughput, what can a junior developer with infinite time and what can that give you in terms of throughput? Where every fever dream that goes through a business analyst's head can become part of your code base. What will the throughput be? And not only, enabling more less technical people to write code, but also as a power user, how much code could you put out? And it's definitely going to be a lot more than it is today. And that's not baking in any of the potential sort of quality breakthroughs that we might see in generative AI. So there have also been lots of studies that talk about the security of LLM derived code. So it's important to just understand that human code is what these tools were trained on. These tools are essentially a mirror held up to the code on GitHub and Stack Overflow. And so if if you have bugs in that code, then when the LLM learns from that, it is going to produce bugs in the same code. And so this is what the studies have shown us as well. But there is some other interesting and probably unfortunate facts here too, that the code looks good, but it is more likely to give an insecure solution for one of the studies, and also paradoxically, developers trust it more because it looks right. It's there are comments that give assurance, and just the form fit gives you the illusion that it may be more secure. And so, I've heard, I think Caleb Seba, who described LLMs as a very confident, overconfident 13-year-old. And that seems really right to me. And this is the kind of statistic that backs that up. So I think, the first, probably for the LLM optimist, they're just going to think, well, look, that may be true now, but won't the models just generate secure code? The models are Anybody who's worked with the models can tell you that the more context you give it, the more likely it is to be, first of all, confused or hallucinate or get the instructions wrong, whatever. But it is interesting to note that a vulnerability is an emergent phenomena across lots of different things: the code, the libraries, the frameworks, the runtime. And so let's look at a typical vulnerability. Data flow vulnerability, something like SQL injection. User input comes into the system and it goes through a complicated path before it reaches sort of the place it shouldn't. And so the idea here, I think, for the LLM optimist, if I try to steel man their case, would be we're going to be able to shove all this code into a context window, and we're going to be able to have it answer the question for itself: is it secure? There are now million token context windows. And so the number of code bases that will fit into context are getting bigger. But there is an interesting point here in that a lot of the data flow, first of all, isn't even in your code. Using embeddings as a replacement for complicated reasoning is not really sort of a valid approach. Embeddings are good for search and for other use cases, but asking to reason very deeply about complex things that it has a hard time about in a very micro case, we're not going to be able to use embeddings to get out of that. Of course, the models, the more multi-step, the more abstract an idea is, the difficult it is for an LLM to model it. And first of all, this is sort of solved. If we take a step back, this problem is not solved well, but I'd say, but it is solved from the point of view of we have purpose-built software that we've been trying to use to find vulnerabilities for 25 years. We've invested many thousands of man hours trying to do this accurately. We have not been able to with traditional techniques. Scan the code, build a syntax tree, ask that model questions, does A flow to B, and it's very difficult, and it's very slow, and there's a lot of branches, and for trying to imagine how a model would come up with understand all the paths that the code actually takes, and follow a data flow vulnerability through that seems very far-fetched based on my experience with both the tools and the LLMs. So I think it's also interesting to think about the incentives for the generative AI tools. So the tools, the LLMs, will be mostly motivated by making developers happy, giving developers what they expect. But we don't always, and so in the other cases in history where you look at, does secure code get rewarded by developers? The answer is no. So as a lifelong security person, I can tell you, usually when you go to Stack Overflow and somebody puts out an answer, the answer is either very incomplete or sometimes wrong. And so in this case, the developer is asking on Stack Overflow, how do I prevent cross-site scripting in PHP? And they give an answer that will work 75% of the time or 80% of the time, but it looks very correct, right? HTML, it says echo HTML special characters. It's sort of, it matches what the developers sort of predicted solution for this might be. But the truth is, it is more complicated. Which cross-site scripting control you choose depends on where in the HTML document the input ends up. Does it end up in an HTML attribute, or does it end up in JavaScript? In those cases, you'll actually want different solutions, and the other solutions probably won't protect you. So life is complicated, security is complicated, and so the easier answer sounds correct. And so if an LLM gives you an easy answer, you may be more inclined to use that LLM versus an LLM that puts out the actual secure answer, because it's going to be complicated and you're not going to understand it, and it's not going to fit your predicted model of what that might look like. A good example of that is trying to stop an attack called external XML entities. It's a really bad attack in XML parsers that allows people to steal the contents of their file system if done wrong. And so in this case, the developer's solution is to switch their parser for something called diffused XML. And they might not know what developer, if they get that suggestion, they might not know what diffused means. And so that's going to be tough for the developer to have to make that decision. So I'm getting some feedback here in the chat that we might be getting some audio problems. I hope it's working, and if not, I hope they're working on it quickly. So look, now we're going to flip back to the software development we have today. So this solution here this graphic is put out by PagerDuty, and it describes all the manual processes that are performed in a secure development lifecycle. And so that's what all these little M's represent. I love this idea, but realistically, if you have a static code analysis scanner that's running on build or on commit, there's a lot of manual effort there too, right? We need to look at the results that come from the static analysis tool. We need to look at the results spit out by our SCA tools like Dependabot or Renovate. And so if there's fuzzing or IAST or dynamic scans or container scans, all of these security activities we do, they do require some manual effort. The developer has to triage, or they have to fix, or they have to talk about. And so, yes, there are some activities they've highlighted as being purely manual, but there's so much manual stuff that happens along the road here. And this is my estimation. Again, I've done a lot of this work. This is where I think a lot of the manual work ends up being in your steady state as well, not just your before the thing starts and in monitoring every day. There's activities that are security activities done. And another interesting part of this mix is that a lot of these activities are sort of cross disciplines. So a lot of times we do have security people who don't know code very well, or code people who don't know security very well. And so trying to ask either of them to triage a static analysis finding is very difficult, because they don't have either one doesn't have quite the perfect background for analyzing the other's sort of aspect of the discipline. And so we've got a lot of manual activities here, and we're not staffed really well for it. We're not, frankly, putting out the documentation, the research into the findings that we should be. And this is really evident if you go to a big company and you look at all their assets. You'll see that if you look at their programs, you'll see they don't have enough humans. I've heard GitHub say that developers outnumber security 100 to 1, and I'd say if you go and look at the enterprises, I think that number is a lot worse. Again, the humans we have aren't cross-skilled, and so if you take a look at the let's imagine that this is a enterprise's portfolio of applications. I think what you'll see is that they most of the time they rank their applications in some risk matrix, and they say, okay, well, this application it's our front end banking application. It is exposed to the internet. It touches the most sensitive stuff we have. This is a 5. And then you'll have other things that are, seemingly less important, and we'll rank those low. And then the unfortunate choice they have to make is they really only spend their activities time on those super high risk assets. And so that's really tough. We're only doing some things for some parts of our portfolio. Now, let's think about sort of what we started off the talk with, which is today, we have these stressors. We're outnumbered at least 100 to 1, probably 1,000 to 1 in the worst enterprises. We have, we're writing 25% more code with Copilot, and there is a, I hesitate to use the word future. I mean, there is a present where we can potentially start writing a lot more code, 100% to 500% more code. How are we supposed to keep up with the robots in terms of security, right? All of these activities, all these M's are done by humans right now. And if we are producing 5 times as much code, how are we going to keep up? So that is the basis for, I'm going to talk about a few solutions here, a few things that I think can scale with the robots. There may be others, but let's just talk about a few because I think they'll give us the pattern we're looking for. So look, we need tactic, strategy. We need to think about this a little bit systematically. And I think one of the things that can help our engineering cultures and at the same time help the robots is to make it hard to be insecure. If it's hard for a developer to write insecure code, then obviously by definition, we will have a lot fewer vulnerabilities. Okay. We did this in our compilers. By the way, we had all these memory corruption vulnerabilities in the early 2000s, and we added, we hardened some of the memory corruption attack vectors by adding stack cookies to our compiled binaries. So Netflix introduced a similar idea called paved roads. And the idea is that we give all of our developers APIs that allow them to just focus on doing their work, but that automatically include security. So, for instance, we might give you an API model to develop on that automatically enforces authentication. You don't have to think about authentication. That will be automatically provided for you. Or we might give you an API to implement that even if it doesn't do it for you, it forces you to think about what is the access control you should be providing. We have maybe a static analysis rule, or we'll have something in our framework that fails either compilation or at runtime when an access control rule is not specified. So in this way, we're making it hard for the developer to make the mistake. One sort of less business logic type of thing, like we can have a rule that we only allow REST plus JSON in our microservice, and this actually does go a great deal towards eliminating a very popular vulnerability class called cross-site scripting. And so another interesting upshot of having patterns like this is that the robot also learns from your code. So a robot will end up delivering code that looks like yours. I don't know if you've experienced this with Copilot. Usually, Copilot wants to write a unit test one kind of way, but then if I have other tabs open where it can learn about the other types of tests I'm writing, usually I just have to write one, and then it starts to understand kind of how I want to do things. And so if we're laying out a lot of evidence for our robots to follow, like these are the right ways to do it, these are the only ways to do it as well, then I think that's going to help a lot. Another more abstract part of this a version of this same kind of thinking is to have we have only a few different types of pipelines in our company, and every one of them forces a static analysis on every bill. So paved roads, great idea, not only to eliminate, make it hard to be insecure when writing new code, but also to help train our robots how to write code. And so we've got some interesting people here to help. Another class of tools that I've worked on in the past have a different strategy, which is to make it hard to actually exploit insecure code when it occurs. It is a when, not an if, that you will write insecure code. And so how we deal with that, how do we deal with that reality? So there is a new class of products called RASP, Runtime Application Security Protection. And so what we used to have was tools like web application firewalls. We still do have these tools. They sit outside the network and they look for malicious input and they sort of make a go, no go decision when they receive the input. And this is tough because these tools are executing outside of the context of the code. They don't know what kind of input the applications want. And so they end up a lot of times being a log only sort of tool. They're not usually blocking because they don't have they're too far away from boom to understand if something is really an attack or not. They're very signature based. And anytime there's a new attack, people are putting out signatures. People are putting out exploits that evade the signatures. And there's another alternative, which is to instrument protections into the application, the framework, the runtime, etc. And so here's an example of a runtime application security protection, an agent that instruments a SQL injection protection into your code. When user input comes into the system, if it was a firewall kind of solution, they'd have to decide based on the input, should they block this? But a agent can take the input, hold it, wait for queries to be called and say, hey, did I see that input go into that query? And if so, did it change the structure of the query? So did data become code? And so you end up with a wildly different level of fidelity on results like this because you not only did you see input that looked suspicious, you saw it go into user data and you saw that overlap of tokens where it seemed to be crossing a boundary. And you saw the input get executed. And so that's a very different way of working and very effective at removing a lot of different bug classes. And so now now there's a lot of vendors who are offering tools like this. So look, the other sort of practical end of this is how can we automate and by the way, I should point out, these, again, we similarly we did this already at the OS layer. We introduced non-executable stacks, non-executable heaps. We used to be a new virus every week, when I was computing in the early 2000s. But we added a bunch of protections to the OS, to the runtime of our operating system, and we eliminated, made it practically impossible to exploit a lot of insecure code. Anyway, all right, back to this. The more practical consideration is how are we going to deal with all the interruptions from tools when we're putting out 5 times as much code. So that essentially means triaging results from security tools and automating sort of the remediation of them. And so we can use tools that we have today to find vulnerabilities in code that um, that the generative AI is creating, right? That we don't need to change anything except use more of those tools as we create more code. And it is possible also to triage the reports from those tools, and it because we can use lots of we can use orchestration of LLMs, we can use traditional techniques to look at the vulnerabilities and decide for ourselves, like, is this a real vulnerability? Because most of the things that come out of tools are not real. And so if we're going to have humans look at all this stuff, not only are we going to be wasting a lot of time, but it will be a waste, because most of the things that they report are not real, and so we'll be wasting it for no reason. Sort of the definition of waste. And so we will also be able to put out pull requests, right? If we can use techniques to find the real things, find the and generate the fixes for those things, then we will be able to uh, pass along our feedback using a virtual product security software engineer, to interact with the generative AI produced code. And if we could have a bot that works with their bot, a bot that works with the generative AI tool, we think that is what is going to actually get us over the hump. That's how we're not going to spend all of our time chasing chasing these bugs down. And at the same time, it's the only thing that's going to enable it to happen anyway, to get the assurance that we need on all the new code. And so I've actually released some of our research here, so I'd like to sort of end talking about that. And so we have an open source project called CodeModder. So code mods were this interesting idea. They were I think it was released by a Facebook engineer named Justin something, who I can't remember right now. Sorry, Justin. And the idea was to build a piece of code, a small piece of code that could change a lot of code quickly. And so it was really cool, but it sort of died. And now the JavaScript community has something called code mods, but they don't really do a lot. And the reason is because it's very difficult to build a code mod library that can identify arbitrary shapes of code and change it to any other shape of code. And so this library orchestrates tools that are great at finding different shapes of code, and existing tools that are great at mutating existing source code. And so this is an example of a code mod or a code mod that orchestrates a semgrep rule. Semgrep is a very expressive um, tool for finding different shapes of code. And our goal with this code mod is to replace random with secure random, right? Insecure sources of randomness with secure sources of randomness. And so we try to make that really easy. All you do is provide the semgrep rule, and then the results from that, the findings from that, are delegated to a libcst, a callback with libcst objects, where all you have to do is make the change that you want to make. And so we're focused on delivering the magic between taking results from these tools, parsing them and delegating them to the right places, and making the changes, making that really easy. And so here are some of the links to look a little bit more into CodeModder. But you can imagine having a code mod that looks at a static analysis result and has the pre-baked solution for what it takes to fix that result. Because a lot of times security changes are actually not that difficult to make. There's usually sort of one right way to do it, and it's usually a matter of flipping security on. And so I think this will be a really cool library for you to check out and build your own stuff on. Okay, look, we spent a lot of time talking about generative AI. I'm excited for the future that it's going to allow. And we are not prepared today to take on the security burden of a lot more code. But I think we have some solutions in front of us, and that's where I'll leave it. I have no idea on time because I know we started kind of late, but I'm happy to answer any questions. All right. Well, if there's no questions, I want to thank you for your time today.